Flutube. Get it straight.
Okay, let's look at a Reynolds transport theorem problem for a simple conservation of mass. So this is one of the early examples in Chapter 4 when they first introduced the concepts. We've got a fire extinguisher of a known volume, known pressure, and known temperature. And at time equals 0, CO2 begins to escape at 300 meters per second through a nozzle of 65 square millimeters. So what is the rate of change of the CO2, not air density, CO2 density in the tank at time 0? So I want to know how fast the density is changing in here. So here's the Reynolds transport theorem, and we've got the material derivative of the system mass, which is equal to 0, because mass is conserved in this system. Here's the system. It's this extinguisher, and it's the mass outside and the mass inside. So it's either inside or outside, but it's not going anywhere else. And so its change in time is 0. So that means that the change within the control volume is equal to the negative of the mass leaving over the boundary if we moved the control surface side over to the 0 side of the equation. So here it is rearranged. So we have the change in the control volume equal to the opposite of the mass leaving the control volume. Now let's assume that the properties in the tank are uniformly mixed. So the density is changing with time inside the tank, but it's not changing spatially in the tank. It's the same everywhere in the tank at a given time. And let's also say that the flow out of the nozzle is a uniform velocity profile. That means we don't have to deal with the integral of the velocity as we move outside the control surface here. So looking at the control volume side of the equation, we have the derivative with respect to time of this integral, density times dV, but density is uniform inside, so we can pull that out, and spatially we're only dealing with this control volume derivative, or integral, excuse me. And so the integral of dV, of course, is V, so we have the derivative of rho times V now. And of those two, only rho is changing, so it's d rho dt. V, of course, is constant for a rigid tank, so there's no derivative with respect to time on the tank. Now let's look at the control surface side. So here we have V dot n, so it's out. So the angle between V and n is 0. Cosine of 0 is 1. And so the velocity coming out is just V times rho, positive V, times the derivative times dA. But we know that's a uniform velocity profile. We said that above, so we can just take that as area. We don't have to do any integration here. So in the end, we have the volume times the rate of change of density with time, which is what we're after in this problem, is equal to the mass leaving the system, which makes sense. That's the only thing happening here. We have mass leaving a system, and it's affecting the density back inside the system. So we figure that out, add the numbers, and get a value of negative 2.34, which says that the density inside the tank is decreasing at that rate. Here's the density units, and it's decreasing per second.